So question 1.1 then. So this question is about silver iodide, okay? This ionic compound right here. And the first question is 2 marks, and all we have to do is define the term enthalpy of lattice formation. So our command word here is define. So this is an easy 2 marker, guys. If you've been doing your flashcards and you've memorized all the definitions that you need to know for the enthalpy changes of atomization, enthalpy changes of formation, lattice dissociation, etc., you should be all good with this question. So all we have to do is define the enthalpy of lattice formation. So let's write that out. Enthalpy of lattice formation. Okay. So what does AQA want to see for this definition then? So if we write out in full here, the enthalpy change when 1 mole of solid ionic lattice, this part is really important, we'll go through the mark scheme in a second, is formed, hence the word formation, giving it away there, from its constituent ions in the gaseous state. Boom, done. 2 marks right there. So from the mark scheme, I'm going to underline the words that you must have within your definition. First one, enthalpy change. Okay, if they're asking you to define some sort of enthalpy, you need to say the enthalpy change when ... Okay, next up is going to be 1 mole. Okay, because the units of enthalpy in AQA chemistry is always going to be kilojoules, so our energy units per mole, it's always going to be when 1 mole of something does something, okay, depending on what enthalpy we're looking at. Next one is going to be solid ionic. Now, I put lattice here because that's how I like to refer to it, but you could put compound or substance or anything like that, okay? Next one is going to be regarding the gaseous ions, right? So this is going to be our next part. So you can say formed from its gaseous ions, formed from its constituent gaseous ions, or how I have here from its constituent ions in the gaseous state. It doesn't really matter as long as you have enthalpy change, 1 mole, solid ionic compound, lattice, substance, etc. And you need to emphasize that it's in the gaseous state, okay? The reactants, so the ions that form it. So an example then, let's look at a real easy one. So sodium chloride. Sodium chloride is a solid ionic lattice. So let's draw that out. Sodium chloride, solid. Boom, done. Right, so what is our enthalpy of lattice formation? We're going to have our sodium ion right here in the gaseous state. Remember, gaseous plus our chloride ion in the gaseous state. Easy as that. So that would be our enthalpy of lattice formation. So question 1.2 then. So they gave us a table, okay? They gave us a table with 3 enthalpy change values that we need to use in the question. And we need to use these enthalpy values to calculate the enthalpy of lattice formation. So let's write this out. Calculate enthalpy of lattice formation. Okay. And what have they given us here? So I'm going to write it out for us. So we're given 3 equations, so 3 types of enthalpy changes, and we're given some values for them. So first one then is silver iodide in the solid state is going to be broken down into silver ion aqueous plus iodide ion aqueous. Okay, next one then, silver ion gaseous gives us silver ion aqueous. Okay, next one, iodide ion gaseous, exactly the same, gives us iodide ion aqueous. Okay, and we've got some associated values for these. Let's put this down. So it's going to be plus 112 here. These are all kilojoules per mole, so I'm just going to put above here kilojoules per mole in case we need that for some reason later on. Next one is minus 464 kilojoules per mole. And the next one is minus 293 kilojoules per mole. So what do we have to do here? Now, hopefully you know this equation already, but if you don't, it's completely fine. But we're going to be using a very simple equation that you need to remember for the enthalpy of solution, okay? So how do we work out what the enthalpy of solution is? The enthalpy change of solution is going to be our lattice dissociation enthalpy plus the sum of our enthalpy of hydration. Okay, this sigma right here, this capital sigma just means sum of. So how does this help us then? So what we need to do primarily is we need to look at these three equations and think, okay, what enthalpy changes are these going to be? So first off, this is going to be our enthalpy of solution because we're turning a solid ionic lattice into its constituent ions in the aqueous form. Whoops, I missed that bracket there. So this is going to be our enthalpy of solution of our silver iodide, okay? And then this one here, both of these two, because they're going from gaseous into aqueous ions, it's simply going to be our hydration enthalpy. So enthalpy of hydration for silver ion, and then enthalpy of hydration for our iodide ion. Easy as that, guys. So this is a really tricky one because what do they want us to calculate? They want us to calculate the lattice formation. But if we glance at our equation right here on the right, this one right here, there is no lattice formation. So what does this mean? Now, the lattice dissociation is simply the negative sign, so the reverse sign of the lattice formation. So let me just quickly explain that to you right here. So let's look at a very simple energy diagram. I've spoken about this before, but hopefully it can help you cement it in your mind. So we've got our solid ionic silver iodide, and we've got our constituent gaseous ions up here, okay? We've got our silver and our iodide. Now, this right here, this energy value, this arrow is exothermic, and that's going to be our lattice formation. And then if we go in the opposite direction, we're going to have our dissociation, breaking up that solid lattice, and it's going to be endothermic because we've got a positive arrow here, so dissociation. Okay, now what this means then, if we look at this lattice of dissociation, it's exactly the same. The energy values are going to be perfectly equal, except one is going to be endothermic and one is going to be exothermic. So all we have to do is chuck a negative value in front of that for it to become lattice formation. Okay, now you can solve this equation with energy cycles, but I find that if you get into the habit of just remembering the equation, it makes answering the question so much quicker than having to draw out the energy cycle. So let's write out our full equation here and rearrange this. So what I'm going to do is I'm going to add a negative in front of this and bracket it up and think of this as our lattice formation, okay? So if we want this to be the subject, we're going to have to take this guy to the other side of the equation. All right, so let's draw that out then. So we're going to have our enthalpy of lattice formation, okay, equals, let's add that H in there. This is going to be our enthalpy of solution. Okay, now we're going to be minusing, because there's a plus here, so minus the sum of our enthalpy of hydration. Okay, now, because this was dissociation and it was negative, and we brought this to the other side, all we have to do is make this side positive, so chuck a negative in front of here, okay? So I'm going to change my color to green, put a negative in front of here, and bracket everything up. Okay, hopefully you guys are confident with maths and you're okay with rearranging equations. So what we can do then is just plug in our values. So this is going to be negative. So what is our enthalpy of solution? I said it's right here, 112. Okay, so it's going to be plus 112 minus. Now we're going to have the sum of our hydration. So our first hydration is going to be minus 464. And then our next one for the iodide is going to be minus 293. Okay, and then bracket all that up. So if you put that in your calculator, you should get a value of minus 869, and that's kilojoules per mole. And that's our final answer, okay? 2 marks right there. Bit of a long question if you think about it, but I still think that if you just memorize this equation and understand the balance between dissociating and forming a solid lattice, you should be fine with rearranging this with a bit of practice. Okay guys, moving on then. So 1.3. A calculation of the enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value calculated in the previous question 1.2, and we have to explain this difference. Okay, so let's write out the keywords of the question. So the formation of silver iodide, so lattice formation of silver iodide. What is it saying here? This is based on a perfect ionic model. So we'll go through what this is in a second. You should remember this from your revision, or you should learn it if you haven't yet. It does pop up. And what is it? It's given us a smaller value than question 1.2. So if we go back to our question 1.2 is minus 869, it's giving us a smaller value, okay? So what I think would be best is for me to quickly run through what the perfect ionic model is, okay? So if we have a substance that is 100% perfectly ionic, we assume that we have perfectly spherical ions involved. Positive cation and negative anion. Okay, they're perfectly spherical, and the theoretical as well as the born-haber lattice enthalpies will be the same. Okay, if we have a perfect ionic model, let's put that out here, perfectly spherical, and then we're going to have the theoretical and the born-haber lattice. So theoretical and born-haber identical. Okay, so this cannot be a perfectly ionic model because they are not the same. It's already told us that it's a smaller value than the theoretical we just worked out in question 1.2. Okay, so what does this mean then? The alternative to this perfect ionic model is going to be covalent character. So we have an ionic compound. This could be silver iodide, sodium chloride, whatever ionic compound you want, but we've got some sort of covalent, this is what they like to call it, basically some sort of covalent action going on, but they call it covalent character, covalent activity, something like that. So what we're going to have here is going to exactly the same. We're going to have our positive cation here, but instead of it being perfectly spherical, what happens is the negative anion, the charge cloud gets pulled slightly towards the positive in a covalent manner. So the electrons get pulled towards this positive and attracted. And what we say then is you would say that the charge cloud is distorted. The charge cloud is distorted. Okay, this is going to a lot more detail than you need for the 2-mark question, but it should hopefully help you. Feel free to skip ahead if you're confident with this topic. So that is the main difference then. So the charge cloud is distorted, and we'll put here covalent character. Okay, this is a very key terminology that AQA love to see. So we've explained the theory. What are we going to do here? How are we going to answer the question? Okay, so it's as simple as this, guys. So I would write silver iodide. You can write it out in chemical form, symbol form, or word form. It's up to you. Has some covalent character. Okay, first mark, easy peasy, guys. If you just remember this, you'll be completely fine. And that's because it's less than the value of the perfect ionic model. Okay, so they can't be identical, therefore it has some sort of covalent character. But what does this mean? This means that the bonds holding the lattice together are going to be stronger. Okay, so it's got the ionic activity and it's got covalent activity on top, so it's going to be stronger. So I would say, therefore, the bonds being ionic and covalent, okay, holding the lattice together are stronger. Stronger. Really important that we say that. So we want to say they're stronger, and we want to say that he has covalent character. Okay, so 2 more marks there. Awesome stuff. So last question here, 1.4 then. So the question reads, identify a reagent that could be used to indicate the presence of iodide ions. So we've got a reagent for iodide ions. What can that be? Okay, in aqueous solution and describe the observation. So typical test tube reaction here. So it's going to be silver nitrate. Okay, hopefully you guys remember the halides here. Silver nitrate. Okay, add it to that test tube, easy XP. And what observation are we going to make? Okay, so with the halides, you're going to have your chloride, your bromide, and your iodide. Okay, very easy color change to remember. Is going to be part of the same color palette, essentially white to cream to yellow. Okay, hopefully you guys remember that, so I'll do it like that. So if you think it just gradually goes from white to yellow and with nice creamy color in the middle. So our reagent, you would write silver nitrate, and your observation would be yellow. Now, is this a yellow solution or is this a precipitate? I didn't mention that here when I should have. These are all precipitates, okay? It's really important that you put precipitate and not just put yellow. You have to define whether it's a solution or a precipitate or whatever the actual observation is. So I love these questions because it's just a case of flashcards. Easy, easy question, 2 marks in the bag, okay? Okay, so as in my previous videos, we also have the examiner's report. I think this is a really important resource that you should all be taking advantage of. And as I said, it will be linked in the description. So I've reworded this to avoid plagiarism and copyright from AQA, but it still covers the main points here. So let's read through this together. So question 1.1. The definition of enthalpy of formation was provided only by the top performing students. Now this is really disappointing. As I said, flashcards, guys, just memorize these definitions. Just remember them off by heart and you'll be fine. It's literally, you see the question, bang, on the page, 2 marks in the bag, move to next question. That's how it should be. You should get into that habit, okay? However, some students failed to understand that a solid was being formed and mistakenly believed that the ionic lattice was created from 1 mole of gaseous ions. Okay, so if we go back to our definition here, it's not from 1 mole of gaseous ions, it's 1 mole of a solid ionic lattice being formed. So if we look at this example here of our, change to a pen, not a highlighter. If we look at our example of sodium chloride, we have 1 mole of this, 1 mole of this, and 1 mole of this, okay? So 2 moles is forming 1 mole, okay? So it's not 1 mole of ions formed 1 mole of solid ionic lattice. It's not the case. Just try and wrap your head around that change. And what else did they say here? Didn't understand it was a solid. Okay, ionic lattices are always solid. Okay, if they dissociate in a solution, they are no longer ionic compounds, they are ionic ions. That didn't make sense. They are ions in solution. Okay, right, 1.2 then. So a significant number of students were unable to correctly determine the sign of the enthalpy change associated with lattice formation. And a common incorrect answer was the same thing, but just positive. So let's go back to our diagram here. Now, as I said, you can use energy cycles for this if you find that's the best way to do it. If you really find it difficult to rearrange equations and wrap your head around that, that's fine. It's a lot more time consuming. When you memorize this equation, it's just on the page, rearrange. Is it dissociation? Is it formation? And then add the sign accordingly, okay? Try and remember this very simple explanation that these 2 things are the same. They're going to be identical. You just switch the sign depending on whether it's dissociation being endothermic and formation being exothermic. Okay, hopefully you remember that. So they got the right answer, the 869, but they forgot about whether it's exo or endothermic. Okay, this is really important. They want formation, therefore we should know it's going to be exothermic, it's going to be negative. Is our answer negative? If so, we should be okay, hopefully, if we did the maths correctly. If it's a positive, we know we've gone wrong somewhere, okay? So 1.3 then. While some students recognize that the lattice had some covalent character, only the most exceptional students were able to make the connection between this covalent character and the stronger bonding involved. So You would get your first mark. You would get your first mark for if you said it had some covalent character. If it isn't perfectly ionic, it has some sort of covalent activity. The AQA buzzword they love is character. Okay, covalent character. But if we have covalent character involved, it not only has the ionic interaction, but it has stronger bonds because you're going to get covalent activity. Okay, shared pairing of electrons. The electron cloud is distorted and it's going to be pulled towards the positive. Okay, just like that. Question 1.4, the last one here. The reagent silver nitrate was widely known. Okay, that's awesome. AS content right here for halides. And most students were able to correctly identify the color of the resulting precipitate. Ooh, precipitate. Remember, it's a precipitate. Silver nitrate. However, some students used a more reactive halogen as a reagent, which was deemed correct but less familiar. So you can do that. You can get your halide displacement reaction tables out and do it that way. But I would highly suggest just chucking silver nitrate on the page. It's a lot easier. But you would get the mark if you did it that way, so it's completely fine. If you did want to do it that way, the answer would be chlorine or bromine, because these are going to displace the iodide ions, okay? So what would our observation be? Our observation would be a brown solution, okay? Brown solution. And sometimes you get a black precipitate forming, so black precipitate. You could add both of these. Either or should be okay. I would focus on the brown solution though, because that would happen every time, because that is the iodine free in solution, giving us that color change. So that's the end of the video, guys. Hopefully you found it helpful. Hopefully you don't find the new format too confusing with not showing the actual question paper on the screen. I would love to be able to, but unfortunately AQA is copywriting, so just keep that in mind. If you found the video helpful, if you learned something, be sure to like the video, subscribe, comment down below. All the best for your revision and upcoming exams, guys. Peace.